To continue on retaining walls, we concluded that if you're going to have here a cantilever wall exposed to active soil pressure here value at the bottom is going to be equal to gamma times h, which means the vertical weight. Gamma times h is going to be the vertical pressure multiplied by the k, and this k is going to be k active. And this pressure here, if you do the integration of this triangular distribution, you can solve for F, the total force, which is going to be equal to the pressure at the bottom divided by the height divided by 2. And of course, there is 1 foot here perpendicular to the screen that you don't see it here because it's just going to be equal to 1. The moment at this face, at section 1, if you like here, this is actually that was the steel location. Along this section here, the moment acting is going to be equal to F multiplied by h over 3. When you cut a section here, take the moment, it's going to be F times h over 3. For this moment, you should be able to design now the wall for this moment acting on it. And of course, your B is going to be equal to 12 inches for the width, and the depth is going to be equal to the wall thickness subtracting the concrete cover. Okay. Now, to confirm the stability, you're going to have here overturning, safety factor for overturning, and safety factor for sliding. This is all about soil design that you should have studied in soil design or foundation design and retaining walls. It's just presented here for your reference so that you understand where is this coming from. And at a certain point, if at any day you'd like to design here a retaining wall, at least you have some reference, you have some material here to do it. But you shouldn't expect this to be in the exam. I'm not going to ask you to design a retaining wall. Design of the retaining wall itself, you have a class for it, and you guys either that you have taken it or you're about to take it. But the only thing that I want you to know here is how to design this stem, which is a vertical wall, based on this moment. So my goal here is to design the structural member, which is a concrete in this case. As I said, usually you take the overturning moment about this point, and you need to have overturning moment safety factor of 1.5 at least, and the same thing for the sliding. If the sliding is not working, you add the key. So this key is to increase the resistance for sliding. We showed also these two forces, active force and passive force. I understand that the passive force is going to be only a resistance, and the active force is going to be the acting force on the structure. At any point, the active force is going to be equal to the passive force plus the friction. So I can add here some friction forces. So I'm going to say here is going to be friction. And again, at any time, this HA is going to be equal to the friction force plus HP. When you run the analysis, in many cases, if this is going to be a good wall or a good design for a wall, this HP plus the friction force is going to be much higher than this active force. And to make it work, the ratio between HP plus the friction force is going to be at least equal to 1.5 times HA. So there is no way that you can say HA is going to be equal to that much, and HP and the friction force is going to be larger than HA. You cannot do this if you like to do equilibrium condition here. But the reality that HA is going to be equal to the friction force plus HP at any time. So the calculated values for the friction force and HP, the passive force, is going to be a resistance, which means to a limit. We have this example. It says concrete retaining wall, and here's the design parameters in the geotechnical report. It says for restrained wall, it's like basement, you're going to have 55 pounds per cubic foot. And they said, we're not going to give you here gamma times h. We're not going to give you here the K value. And instead of giving you Ka or Kp, and instead of that, we're just going to give you here Ka multiplied by gamma right away. So this value here is equal to Ka. This is going to be restrained, which means K sub 0. So this value here is going to be Ka multiplied by unit weight. Which is gamma. Same thing. So difference between this case and that case when you have level backfill and when you have sloping backfill. If this is not clear, I'm going to take you back here and show you the difference between level and sloping backfill. This is here sloping backfill. Sloping backfill, sloping backfill, sloping. This here is going to be level backfill, which means when it's straight. This restrained wall means that you are going to have here a basement wall. Basement wall is going to be like in this case. Like in here. So you're going to have two supports, and this is going to act as simply supported structure member. This wall here is going to be acting as simply supported structure member, supported in two supports, and it has some loads coming here from the side. All right. It shows here some discussion about the reason about this unrestrained versus restrained. Unrestrained is going to be for this cantilever system like this wall. Restrained is going to be for this system of a basement. When you have a basement and then you have concrete slab on the top. They say here unit weight of the soil is going to be 110 pound per cubic foot. Coefficient of friction is going to be 0.4, and the passive pressure is going to be 350, which is going to be coming on this side. One more thing that you need to work on. Concrete strength is 2500 psi, grade 60, and they say design the vertical reinforcing of the stem. This is going to be the stem. Consider number 5 rebars, and for sure the rebar location is going to be on this side. All right. So this is going to be one good question here. If you need to add the reinforcing in the retaining wall, do you think it's going to be in the soil side or the air side? So I'm going to call this to be soil side. And this is going to be air side. What do you guys think? With the reinforcing, the vertical reinforcing of the wall, do you think it needs to be in the soil side or air side? Okay, soil side. Just remember this. It can be one of these questions that you have maybe a couple of points just to know the difference between the two. Where to put the reinforcing part. Okay, good. So let's find out the pressure on this wall. So the section of the wall is right here. Now, when I do here the active pressure, should I do it for 10 feet or should I do it for 12 feet? And here's my reason for this question. I'm gonna take you back here to one slide that we worked on, like this one, or like this one. You see where the active pressure ends? It ends all the way at the bottom of the footing. But this case here, it is made specifically to study the stability of the wall. But when you look at this stress distribution or the active pressure, is to design the stem. So you don't really need to take it all the way down for 12 feet. You just take it here for 10 feet. So we say here, we're going to treat this as the 35 pound per cubic foot, which is this number here, unrestrained, it's cantilever wall and level backfill. So it's going to be 35 pound per cubic foot, leveled cantilever. And the pressure at the base or at the bottom of the wall, at the end of the wall at the bottom here, is going to be equal to 35 times 10 feet, which is the height. So this here is going to be the soil pressure, hydrostatic soil pressure, if you like. And this is going to be 10 feet, which means the depth of the soil to the bottom of the wall. So right here, I have 350 pound per square foot. Now, how about the force? I need now to do integration of this stress distribution. So I'm going to be taking here 350 times the height, divide by 2. And of course, there's multiplied here. There is a factor of 1, which is like a foot perpendicular to the screen. So I have total of 1.75 kip. This is going to be the total force. This force here is going to be at the surface level. We call this H. So when you look here at the code, concrete code, you look at this type of force, they call this soil pressure. Soil pressure, we use the symbol H. The load factor for this H is going to be 1.6. It's going to be very similar to the live load. The moment here at the base of the wall is going to be equal to 1.75, and here's the force, multiplied by the moment R. And this moment R is going to be from here to there, is going to be equal to 1/3 of the wall height. This is the reason that I have 3.33. This is going to be 10 divided by 3. This is going to be the moment R. So the total surface moment is 5.83 kip-foot. You have the load factor times 1.6. You have 9.328 kip-foot. After that, it's going to be same as any reinforced concrete section design when you don't have compression reinforcing and you just get a rectangular section. In the problem itself, it says cover is going to be 3 inches. So I'm going to say the depth here is going to be equal to 9 inches. I'm going to put it right there. It's given on this side. So 3 inches from the face of the concrete wall to the reinforcing bars. And then after that, the depth is going to be equal to 9 inches. I'm going to try here number 5 at 16. If you guys remember, we said that your maximum is going to be 18 inches, but usually we would like to keep it max to be 16 inch. So we said number 5 at 16. Why number 5? Because in the problem itself, it says use number 5 rebars. That was assigned to me, so I cannot change it. And I want you guys to know, like in the second midterm, when I gave you number 7 rebars to be used, you cannot change it and use, let's say, number 9. If this makes sense to you, I asked you to use number 7 rebars for the bottom reinforcing of the footing, meaning you need to come up with your choice based on number 7 rebars, not to number 9 rebars or number 8, if this makes sense. So now we have the moment, we have the depth, and after that, it's going to be a very simple problem. You just need to design for the reinforcing. So now let's look at what happened. Here's the reinforcing bars, AS. One rebar number 5, it has 0.31 square inch for just one rebar. This is going to be AB for one rebar. And then you divide here by the spacing, multiply by 12, because you're going to be taking a strip of 1 foot of the wall. You can find here the compression block depth, and look here what happened for B. We're using here 12 inches. Concrete strength, we say it's going to be 2.5 KSI, 0.85, and the reinforcement is going to be 0.23 square inch per foot. So I used here a foot. You see here A is going to be very small, which means your phi factor is going to be equal to 0.9. This is one thing that you need to confirm. Now phi min, the phi factor is going to be 0.9. Amount of steel equals 0.24 square inches. It's about 0.24, 0.23 if you just run the numbers. Fy is going to be 60 KSI. The depth here, as you see here, it says 8.5. So I understand someone's going to say, but it's going to be 9 inches. Just to be a little bit conservative, it's okay to reduce it a little bit. Because someone's going to say here, when it says the clear cover, if I may come here, when it says the cover is 3 inches, let me put here a rebar. Let's just give it some thickness, right? This 3 inches is going to be the clear because it says the cover. Cover means the clear. So from here to there, this here 3 inches. And the rebar is going to be number 5. So someone can say the actual depth, if I'd like to go very exact, right? I'd like to be very detailed. So I was going to say it's going to be equal to 12 inches minus 3 minus, I'm going to say here, 1/2 of the bar diameter. The bar diameter is 0.625. Why? Because it's going to be number 5. Number 5 rebar is going to be 5/8 of an inch. You're gonna say divide by 2. So in your analysis, maybe you'd like to consider here half an inch, because quarter of an inch is gonna be very small. You can just round it up to half an inch, especially that's gonna be a little bit conservative. So you see here, the depth equals is gonna be 9 minus half an inch equals 0.85 inches. This is the reason that in this slide here, the depth is shown like 9 inches. Very quick estimate, but if you like to go detailed, maybe you like to go with 8.5 inches. And of course, you divide here by 12 to put it in cubic foot, and you see here your demand is much less, right? How much is your demand? Let's look here, 9.328, and your capacity here is gonna be 8.88. So this is not good. Maybe you'd like to add some more rebars. So we're going to be doing here number 5 at 14, because the problem itself, it says consider the use of number 5. So don't change the rebar size, just reduce the spacing. Again, the 0.31 is going to be AB. The 14 is the spacing. You divide here by the spacing, and then you multiply by 12, because you're going to have here 1 foot strip. And here we go. Now the reinforcement becomes 0.263. Previously, the reinforcement was 0.23 to 0.24. Now it becomes 263. Now it is higher. Find out A. Now A is going to be a little bit larger. Find out again C over D. Confirm that phi factor is equal to 0.9. And then you find out here phi man. Same exact equation. You just change here the A value and the AS value, 263. Now look what happened. Phi man now becomes 9.68 cubic foot. The demand is 9.3. Now this is going to be a good design. So the reinforcing bars provided in this retaining wall is going to be number 5 at 14. Number 5 at 16 was not good enough. Any questions?
No questions here. All good.
All good. All right. So you're not going to see here the depth that you use in the final is going to be, of course, something like 8.5, not this 9 inch. So I'm going to say this 9 inch is kind of rough estimate. So I'm going to cross it out so that you guys keep this in mind. I'm going to say, let me make it here 8.5 inch, since I'd like to do here a good job in figuring out the amount of reinforcing, right? And just, you know, this section here, or this example, you're not going to see a practice problem on it. I'm not going to give you here like a submittal to do this retaining wall. But this is a very simple example for you. You have the soil pressure, right? You have the wall height. You can figure out the moment, ultimate moment. And once you do the ultimate moment, you design the rectangular section. So you should expect something like this in your final. So this here is going to be in your final. So if you're listening, or maybe you're going to be studying, and then you can watch the recording. So you need to know there's going to be a problem exactly like this in the exam. But it's going to be a little bit different. I'm going to change the height, I'm going to change the wall thickness, rebar size, and just ask here to find out the ultimate moment, which is this moment here. And then after that, you're going to be doing AS. So this part here, you have done it a few times, many times by now, right? Design of a rectangular section for some moment. So the only thing is going to be a little bit different is going to be this trick here. If I give you the soil pressure, can you find out the ultimate moment on the wall section? All right, any question? Now the last slide said it's going to be about shear walls. But when you open the code, the ACI again, it doesn't say shear wall. The ACI code just called it structure wall. And then they have limits. They said if you have too much shear, here's the treatment. Here's the way that you're going to be designing this wall. If the shear is going to be very low, which is less than 50% of PVC, you're going to have different type of treatment, which means you're going to treat it as gravity wall. So what is a shear wall? Shear wall is going to be that concrete wall that you put in a building to resist seismic forces and wind forces. Seismic forces and wind forces means like forces due to earthquake or forces due to pressure, wind pressure. And this force is going to be a horizontal force, meaning I'm expecting the horizontal force to come this way, right? Or it's going to be coming this way. Because you cannot control what direction the earthquake is going to be pushing your building. So it can happen in both directions, longitudinal direction, transverse, or X and Y direction if you like. The same thing here. So if I'm going to put here some force coming in this direction, and look here, the force can be coming from east to west or west to east, because when the building shakes, it's going to be going right and left, meaning that the force is going to be coming in both directions, right? So when you put the force here in this direction, in the X direction, these two walls will be supporting this force. If your force, the seismic force, is going to be coming this way, these two walls is going to be supporting this force. Same thing here. How about here? You say if the force is coming this way, these two longitudinal sections of the wall is going to be taking the force. And if the force is coming that way, in the Y direction, it's going to be these two walls in the Y direction. Meaning that here the wall is going to be resisting the force in the strong direction, not in the short direction, if this makes sense, of the wall. Same thing here, different type of walls. Again, if the force is coming the X, it's going to be all of these walls in the X direction on the perimeter is going to be resisting that force. And if you put it in the Y direction, it's going to be all of these walls in the Y direction will be taking this seismic force. So here's again the force. You have Vx and Vy, we call it base shear. Base shear means the seismic force acting on the building. So this is the reason that we call it V. So we call this base shear. Base shear, it is not a shear in structure member. Base shear means the seismic forces, earthquake forces. So when the force is going to be in the X direction, the two walls resisting it is going to be SW1 and SW2. When the force is coming in the Y direction, it's going to be walls SW3, 4, and 5 is going to be taking this force. Distribution here of the force is going to be an issue. Now it's going to be equal. How about in this direction? Is this going to be taking more than this two, or this going to be taking more? So there's lots of analysis that can be done on this. And of course, it's going to depend on this concrete slab, the rigidity of the slab, the concrete slab here. Also depends on the stiffness of each one of these walls. And as you know, the stiffer wall is going to be sucking more load because it's going to be moving less, because it has higher resistance. There is another system of buildings at which you have shear walls in one direction with maybe some moment frames. So it says here MF1 means moment frame. And in the Y direction, you have only moment frames. So when the force is coming here in the X direction, you have 4 elements to resist that force. You're going to have 2 shear walls and 2 moment frames. But for the Y direction forces, you're going to have only moment frame 3 and moment frame 4 to be taking the force here in the Y direction. It's going to be that simple. So, okay. How about the ACI code? The ACI code, it says here, I'm going to call it structure wall and not a shear wall. But since it has higher shear force and higher shear force demand on this wall, I need to do the following. It says here you need to have 2 curtains of wall reinforcement, which means 2 layers. If the shear, which means the force in each wall, is going to be higher than 2 square root of F prime C, This ACV is going to be the sheared area of the wall. We're going to be talking about this. And of course, F prime C is going to be the concrete strength. Also, they say here that all the continuous reinforcement, horizontal reinforcement, vertical reinforcement, it needs to be anchored or spliced. You guys remember the hook, 90-degree hook, 180-degree hook, and the splice length. So you need to follow this requirements. We have specific requirements for this splicing and anchoring the rebars. They say also for these walls that we're going to consider here to be shear walls, minimum steel ratio, vertical, horizontal, it's going to be just one value. So if you remember in the previous lecture, if I may go back here, you have this table that includes the steel ratio, but this happens when V sub U is going to be lower than 1/2 of PVC. Now, once the shear demand is going to be going beyond, it's going to be more than 0.5 of PVC, you cannot use this table anymore, and you're going to have only one value, which is 0.0025 as a steel ratio. The spacing again is going to be 18 inch, right? 18 inches is going to be the maximum spacing. And for sure, you'd like to use maybe 16 inch. I have here some examples for you for an actual shear wall from a building to a parking structure. So you have here 2 concrete slabs, you have 2 levels. This is going to be the podium level, like the concrete slab on the top, and then you have parking level here, level A, and then parking B is going to be on the grade at the bottom, all the way at the bottom. Here's the shear wall. Looking at the elevation of it, it says here is going to be 12 inch thick. And for the wall rebar itself, it has number 6 at 16, each way, each face. So this means each way. Each way means in the vertical direction, horizontal direction. And then at each end, you're going to see here number 8. We call this jamb bars. Now, you understand that the force is going to be coming like this from the seismic, from the earthquake. Same thing here also, you're going to have another force. Meaning that your moment is going to be in this direction here. So this side is going to be compression and this side is going to be tension. If you remember in beams, you'd like to put the rebars all the way in the tension side. So I said, okay, let me put here number 8 for tension side. And this is going to be the most effective location of the rebars when you put at the end. So someone's going to say, how about this number 8? Why would you put compression rebars to be the same as the tension rebars? You say, no. This is also going to be tension rebars because the earthquake, you cannot control the direction. The earthquake also can be coming in this direction. So the earthquake coming this way, this is going to be the tension rebars, this is going to be the compression rebars. Okay. Here's the end for the jamb reinforcing. As it says here, jamb rebars. It's going to be this big rebars at the end. As it says here, number 8. So look here at this elevation, it says here number 8, and here's the section. Here's the 8 rebars, and then you have some ties around it. The number 6 is 16, which is the wall rebars, is going to be here. This is going to be like the wall rebars. So all of this rebar, horizontal and vertical, is going to be this rebars here. Number 6 is 16. The number 8 is going to be at the end. And here we just showed as a line, but in reality, it's going to be a cluster of rebars, 8 rebars, as you see here, with some spacing, given spacing. I said, okay. Now let me conclude here what the code says. Code says minimum reinforcement is going to be 0.0025. Maximum spacing is going to be 18 inch. Right? And you need to have 2 steel layers. One, the concrete strength. This is going to be the concrete strength, right? Only the concrete strength, VC. One VU is going to be more than the concrete strength. And we just consider here the concrete strength with a factor of 2. This is what we call here the shear factor. Any questions?
What was ACV again?
ACV is going to be the section of the wall that you're going to be cutting through. For example, let's say that I'm going to be this shear force, I'm gonna call this here to be V, is gonna be acting on this wall. So I'm gonna say the shear section of the wall, if I may do it here in 3D, is gonna be like this, right? It's gonna be a section of the wall, horizontal section. So this dimension is gonna be equal to the wall thickness, and this is gonna be the wall length. So if the wall length, if I may use here, L sub W, which means the wall length, and the wall thickness is gonna be TW. So I'm gonna say here A CV equals LW multiplied by TW. So as if you're cutting a section through the wall and then you look down and then you tell me how much cross-section area are you looking at? Because it's gonna be the section here exposed to shear. So again, this ACV is gonna be equal to the wall thickness multiplied by the wall length. This one you do it for the entire wall. Any other questions?
This may be past the class's spectrum, but what happens like if it comes at an angle, not straight at it? 'Cause
Okay, very good question. I'll tell you what's gonna happen. Let's say the earthquake here comes in a direction like this, right? Let's give you your question.
yes, that's my question.
So I guess I should be able to resolve the force in two directions. One component is going to be in the x direction, and the other component is going to be in the y direction. This component, you can call it Vx. This component, you can call it Vy. So when the earthquake here comes at any angle, you can just resolve it into two components. It's going to be that simple. Usually, you're going to have a software to do this for you, to do the distribution. When you practice, you're going to have a software for it. But you need to understand the basis of it, where this comes from. And the other question is, do you really need to do this or not? Or just do it in the x direction once and the y direction once? This force in the x or
Wouldn't
the
you
y
need to
direction,
check?
what's that?
I'm saying, wouldn't you need to check? Because what if you don't, one wall's not able to sustain it?
This is correct, but also you need to understand that the force in the x direction and the force in the y direction, usually they're the same. It's gonna be exactly the same value. So let's say you have here 100 kips. And in the y direction here, you have 100 kips. About in an angle, you're gonna say, okay, let me do it here as 100 kips. So if you do it in an angle and you resolve it into two components, do you think that any of these components is gonna be 100 or it's gonna be less? Now let's say you have one force here, which is this one, and you don't have any other components. You can say it's gonna be like this. Now we're gonna resolve it in the x and y direction. Now each component is gonna be less than 100 kips. Let's say if this is gonna be on 45 degrees, you're gonna have here, let's say 70 kips and 70 kips. Versus when you design it for a total of 100 kips in each direction, x and y. So this design here for the x and y direction should be sufficient. And you don't really need to do this on an angle unless you have one of the walls is aligned in this direction. Meaning I have one wall like this. Let's say I decide to have a wall like this. Right? So in this case, I need to try the force to be parallel to it in the same direction as this one. Otherwise, it is sufficient when you do it in the x direction once and the y direction once. Don't forget, the force is not acting in the x and y direction at the same time. The earthquake, usually, the shaking is going to be coming in one direction only at a time. Any other questions? All right, I guess we can finish for the day, and I'll see you next time. Please go ahead and sign out.
Okay, thank you.
Thank you.
Or so do you want us to sign?